SwayamPrabha. Digital India. Educated India.
Yeah, and various systems also. For example, the first one what we discussed was this gas solid reaction, right? Yeah. So, gas solid non-catalytic reaction. Right. So, the example which we have taken was carbon solid plus O2 gas giving us CO2 gas, and the model imagination is something like this. So, we have solid, we have this is carbon, then we have film, and all around we have O2, and O2 has to diffuse to the surface and CO2 has to come out. And we have also written the equations like sorry, this also can be modeled like this as solid, this is the film, right, gas film, and then if I draw the profiles, this is CAG, that is the concentration of oxygen in the gas phase. Then I may have something like this. This is CAS, right. So, at steady state conditions, the amount of oxygen which has diffused through the film must be equal to the reaction that is taking place on the surface. So, we have written that, and then the equations what we have written was that minus R A equal to Kg CAG minus CAS, and if I assume I have first order reaction, this is Ks CAS. Okay. This also we have written. So, now the global rate of reaction or observed rate of reaction, this also okay, is defined as the rate in which only the measurable variables are present, right. Here the measurable variables is only CAG, and I cannot measure the concentration on the surface which is CAS. We have to why means, because here I have to put some probes and then try to find out how many moles of oxygen staying on the surface, right. So, that is not that easy, and that too it is very hot surface. So, any technique which can be used on the surface is normally very costly technique. Only for that this Ertel from Berlin University, he got Nobel Prize to show that how to measure the concentration on the surface, and he used the examples like on the platinum surface CO is getting oxidized as CO2, that example that is one example. Another example also ammonia, how hydrogen molecules are at least getting adsorbed on the surface and how they are reacting. The actual reactions he could show by constructing his own equipment, that is why he got the Nobel Prize. Exactly, that is surface phenomena what you could show, that is available on his website. If you want to go and then see that, Ertel, ERTL, that is the Nobel laureate name. So, if you go, you can also see that it seems during the reaction on the surface there are waves also generated, that waves also he has picturized. So, that is why of course, he got Nobel Prize. Okay, good. So, that is why this is very difficult technique to measure on the surface, and as I told you, as engineers we should see that as simple as possible we should use the technique. So, that is why best thing for us is elimination of this, and if we eliminate this and then try to write the equation, that means I can take these two, CAS is eliminated. So, if I eliminate this, let me write the other steps also, Kg CAS, Ks CAS. So, then I have CAS equal to I am jumping the steps, equal to Kg Cag by Kg plus Ks, right. Okay. So, now this if I call this one as 1, 2, equation 3, then equation 3 should be substituted in equation 1, because either this or this, any one of the terms. Then I have minus RAOB observed rate equal to, if I substitute here in this Ks, I have Ks, Kg, Cag divided by Kg plus Ks. This also can be written as Cag divided by 1 by Kg plus 1 by Ks. So, this is the rate expression. That is the rate expression for coal combustion, and this rate expression is peculiar here, because we have a mass transfer coefficient Kg and also we have a reaction rate constant. So, in general, when you are talking about chemical reactions, we never take mass transfer coefficient into account, but still here in all heterogeneous systems, mass transfer coefficients will be automatically coming into picture. And if you remember my picture, the famous picture which I draw here, this is reactor, input, output, kinetics, contacting, here we have chemical, physical, and here we have batch, continuous, and in batch again we have PF and MF. So, this part we have understood what is batch, what is continuous. In continuous, when do you choose PF, when do you choose MF, all that we have discussed. Now, when you come to this, there are two terms, chemical and physical. Chemical is the one which represents Ks, physical is one which represents Kg. So, that is why here you have both chemical as well as physical. That is the meaning of this diagram, right. So, that means most of the time, I have already told you some time back that most of the combustion process, this is coal combustion, most of the combustion processes are mass transfer controlled. The reason is that the temperatures are very high. So, this Ks is very large, because Arrhenius equation. So, when Arrhenius equation you have small change in temperature will be creating large coefficient, and now at very high temperatures this is very large. So, at high temperatures Ks is large tending to infinity, just as an example. Then we have minus RAOB equal to Cag by 1 by Kg or Kg Cag, which we can write as mass transfer equation, which is equal to 0. So, this is 3, 4, 5 and then 6. Now, you see, if you assume that for this gas phase you have plug flow, we have to choose the contacting. So, if I am now thinking that my gas O2, this is minus A is O2, right. So, this is moving in the form of plug flow. So, what is the equation we use here for the contacting? V by F A naught equal to 0 to x A dx A by minus R A, minus R O B. So, now I have to substitute this equation, that is 0 to xa dxa into kg CAG. This is a reactor design equation, but still we have only mass transfer coefficient coming into picture. Okay? Yeah. So, similarly, if I have both the controls, then I will have this equation CAG divided by 1 by kg plus 1 by ks, that is what is here. So, on the other hand, if I have at low temperatures or reaction rate is slow, at low temperatures kg will go to infinity, that means when compared to ks. So, this here also I will write this is mass transfer control, and this is reaction control. Yeah. So, when kg is very large value, from equation 5, from equation 5 minus RAOB equal to, we have CAG, this goes to, this goes to 0, 1 by kg, and then I have Ks 1 by Ks, which is nothing but Ks CAG. So, this is equation 7, this is equation 8. Yeah. At low temperatures the reaction may not be that fast. Ks is less, reaction is not fast, right, at low temperatures. Okay. So, that is the reason why kg relatively is faster when compared to ks, right. So, that is the reason why kg will be very large value. So, 1 by kg is neglected, then it will be only ks, which is reaction control. I have been giving you this simple example like your hostel food. Okay. I think assuming that you have conveyor belt for breakfast, from the kitchen you send the they will be continuously feeding, let us say idlis. Okay. So, idlis will be put there on the conveyor belt, you are there just around the conveyor belt, and then as soon as idlis come on the conveyor belt, if you are very hungry, what will happen? You will eat, right. So, practically on the surface what will be the concentration? 0, you will not have anything. Now, which is controlling now? Which is the controlling? Is it the supply of idlis, or is it your eating which is equivalent to reaction here? Supply, mass transfer is controlling. Okay. On the other hand, after eating maybe everyone 50 idlis, you cannot eat anymore, right. So, then you will have everywhere concentration, that means your rate of reaction, rate of eating is almost 0 now, very slow. Even if you eat, because someone is putting a gun and then say that still you have to eat. So, then for the sake of eating you may take only piece of idli, and then still you are eating, but the rate is very low. That is what is reaction control. It is relative, both are relative. Whenever we talk in this cases both are relative. If both are equal, then this is the equation which you have to use. Okay. Always in the controlling steps, the lowest step will have the control, slowest step. Okay. In these steps, these are simple examples which I give. So, in these steps the slowest step controls. Here the slowest step is mass transfer, because reaction is very fast, and here the slowest step is reaction, and mass transfer is very fast, and as you said these are all relative. Okay, good. So, now this is the equation what we use, and here we are comfortable, it is Ks CAG. If I take, it is like our first order reaction, right. So, we say order of reaction with respect to concentration. In this case it is first order with respect to oxygen. If I want to use in the design expression, again I go here and substitute, this time I will have Ks and CAG, and CAG is measurable. That is why we call this rate as observed rate, observed, or another name global, another name measurable, very good. Is there any other name? Measurable or observed? Observed I have given, observed, global, measured, overall rate of reaction. Okay. So, rate of reaction. So, all this will come there, because when you have heterogeneous system, you cannot avoid this observed rate or global rate or measured rate. Why we are telling observed rate is, we are able to express this equation 5 in terms of measurable quantities. CAG is measurable, and 1 by this kg, I should have some correlations. Any one of you know what are the correlations we use if I have single particle and then mass transfer is going through this particle or to the surface or inside the surface through the film? Have you come across that equations? Single particle, we have just only one particle, and around the particle oxygen is going, and this oxygen is going to the surface of the particle through the film. It is external film mass transfer. Not able to recall? There is one equation called Runge-Marshall equation. It is in the 3rd chapter of Tribal. Okay. And of course, Lewon's-Piel non-catalytic reaction also he has given that, he calls that one Runge-Marshall, but Tribal calls that one as Froseling equation. Froseling equation. Okay. So, that equation tells us that we have Sherwood number equal to 2 plus 0.6, Reynolds to the power of 0.5 and Schmidt to the power of 1 by 3 or 0.33. That is the equation. Okay. And I think I have to tell you here, because most of the time now we will be talking about mass transfer coefficients. This is one of the simplest equations in chemical engineering, for because it is a single particle, and in reality you will never have single particle, right. And in multi-particle systems, developing this equation is not that easy, mass transfer equations. That is why a lot of researchers have spent lot of time to develop the correlations. Even now people are developing if it is a new system, and surprisingly in chemical engineering, if this is for single particle, and I cannot use the same thing if I have packed bed. The mass transfer through the packed bed is slightly different, and if I take fluidized bed, that is different, and all the equations are in terms of only Sherwood number, Schmidt number, Reynolds number. You take any equipment like packed bed, fluidized bed, moving bed, your rotating drums, all these things, the mass transfer equation contains only Sherwood number equal to the function of Reynolds number and Schmidt number. That functionality we have to find out only through experiments, right. So, that is why if you have the same process what we have discussed here, if it is in fluidized bed, then you have a different mass transfer correlation. Kg I am talking, this Kg, because Kg is here in Sherwood number. I hope you remember Sherwood number and Schmidt number. Reynolds number everyone remembers. That is only one number most of the time chemical engineers remember. That is why in my interview, whenever I sit for interviews and all that, I ask them, other than Reynolds number, please tell me another number. And it is really funny, particularly there are also numbers in fluid mechanics. So, other than Reynolds number, we cannot list out any other number in fluid mechanics. Other numbers, of course, very famous numbers next to Reynolds number is Schmidt number and Prandtl number. And why all these correlations should have Reynolds number and Schmidt number, and here we have even heat transfer coefficients also same, exactly same thing. Here we have Nusselt number equal to same 2 plus 0.6, Reynolds number will be there, and this will be Prandtl number. That is the reason why you study transport phenomena, because transport phenomena tells you that all these transfers have some kind of similarities, some kind of same phenomena. So, that is the reason why in transport phenomena, you have the famous correlation JD equal to JH equal to F by 2. Why do you need that analogy? We know, we know that equation, but why do you need it for heat transfer?
Mass transfer and heat transfer relation.
Yeah, fluid mechanics also is related. F by 2. JD equal to JH equal to F by 2. F is friction factor by 2. And we need that kind of thing as engineers. If I do not have sufficient time to find out mass transfer coefficient, I can use friction factor. But there are many conditions for that analogy, right. Under those conditions, I do not have to conduct separate experiments for heat transfer or mass transfer. If I know any one, if I know JD, I can calculate again friction factor. If I know JD, I can calculate heat transfer coefficient. JD is for mass transfer, JH is for heat transfer, and F is friction factor. That is why that analogy comes automatically for us. That is why I told you, chemical engineering is great. The analysis, the principles wonderfully demonstrated all the time through equations. But only thing we do not know is that where they are applicable. Because I think in 50s and 60s that was excellent period for chemical engineering. The reason was that the chemical engineering and industry work together. Beautiful love marriage. Yeah, but after some time in 80s, divorce. And the catalyst for divorce is, you know what? Can you guess? Transport phenomena course. That is the one. Because when transport phenomena, that book was first published in 1961 or 1962 by Bird, Stewart, Lightfoot, it really changed the thinking of many engineers, not only chemical engineers. Mechanical engineers use that, civil engineers use that, and metallurgical engineers use that. Many people use that phenomena, this transport phenomena. Then people thought that, particularly in academic institutions, people thought that excellent, now any system in engineering now I can model. Till then it is only empiricism. Do the experiment, develop the correlations. That is what, because of that only this correlation also has come. Later these coefficients have been justified by transport phenomena through boundary layer. Theory has come there, theory also explained there. But it was wonderful, in the beginning, that empiricism means you have a feeling for what you have done. And theoretical, highly complicated equations you solve, and then finally you find out those coefficients which may not be exactly like you measure. And of course, any theory should be validated by experiment at the end. So finally what has happened was, many academicians thought that they can happily publish and get away without worrying about what is happening in the. And when an industry person comes to an academic institution, then the industry person was asking some questions, and the moment he asks a question, the professor always replies in terms of differential equations. And differential equations, industry person has forgotten long time back. So that is why he thought that, my God, all the professors started talking a different language. It is not industry language. So that is why the distance between those two increased, and that is when in some industries they started industrial research. That means their idea is to solve immediately the problems, not like academicians. Academicians, they take a problem and then they have their own pace, because they do not worry about industry, and time is not money in academic institution, whereas in industry time is tremendous money. 1 hour gone means maybe $1 million also you may lose. So that was the time when these people have become that divorce, they are divorced. And now of course with nanotechnology and all that, I think no industry can understand what we are talking. So that is also, that is the greatest contributions what we have with these new technologies. So that was the reason why we are not able to get more, a lot of consultancy and all that, particularly in chemical engineering. But in other engineerings like civil still lives with a lot of empiricism. They have called, I told you, one God's boon called factor of safety. Their factor of safety may be 5 times, 10 times also. Do you know the reason why their factor of safety is high? Our factor of safety may be only 10% or maybe 50%, right. I think in Maccabee-Thiele method, Murphy efficiency, normally how much you take? You calculate it theoretically 10 plates, right. Yeah, divide by 0.8, that means 20%, yeah. Otherwise sometimes 50%. The reason is that you are not confident about your mathematical analysis, because there are many assumptions. Like that in civil engineering, there are many things. First of all, brick, they have to assume some, and every person produces brick in a different way. So how can you generalize that? Then the concrete, what they make, the gravel, So, theoretically it may be only half an inch particle, but I think it will vary from 1 nanometer to 1 kilometer maybe, I am just exaggerating. Yeah. So, then where is the theory coming there? On the top of it cement. Cement they specify something, but you know, particularly in India we are great in mixing things. So, ash will be mixed with cement. So, then that also gone. So, that is why the factor of safety anyway finally building has to live at least for some time, no, or bridge or road whatever. So, that is the reason why factor of safety is very very high in civil engineering, but whereas factor of safety is minimum in aerospace engineering. If they calculate 100 tons of weight finally for the flight and okay, factor of safety equal to 0.50%, okay, yeah, then weight will be 200 tons, it will never fly, it will only go as bullock cart again on the road. So, that is the reason why that factor of safety is less for sophisticated things, and electronics also. I do not think electronics they do not have any factor of safety in electronic industry, okay, because the problem there, advantage there with electronic industry is gravity will never bother them, correct, no, it is only electronics flowing in this way, current will come in this way, but where is the gravity coming there? Gravity will never affect. But in chemical engineering, in civil engineering, mechanical engineering, metallurgy, gravity affects, and systems are generally very difficult, because gravitational force you have to take, no? And because of this gravitational force also we talk about again buoyancy and all that, right, and buoyancy we know what is buoyancy, but we do not know how to really apply for our calculations. So, because of all these problems, that factor of safety and all that will come there. Okay, anyway, so that is why this equation is one just I have written, but I will write many more like that. Why I wrote that equation is from this you calculate what is the equation for Sherwood number? Kg dP by capital D, which is diffusivity, dP is diameter of the particle and kg is the mass transfer coefficient. From here you can calculate that kg, substitute in equation 7 and then we can integrate, because this is the simplest integration. Then you will get your volume of the system. I mean in a simple design, I am not saying that all combustors are designed like this, but I want to connect that diagram where kinetics and contacting both we can take. So, that is the reason why I am trying to tell the simple examples. They are not real examples in the sense that real examples I will tell you when you come to non-catalytic reactions. Okay, good. So, this is how. Now, let me also tell you here in this profile, if I have reaction control, maybe I will draw here. Again the profiles we will redraw. This is solid, that is carbon, then this is the film, and I have here CAG, this is what I know. This is bulk. In bulk there is no concentration gradient. Okay. So, there is no resistance for the assumption is there is no resistance for the molecules to go through that film. So, that is why it is constant. From there if I have reaction control, how do I draw that profile? That means you have to come here. If it is reaction control, the equation is this one, Ks CAG equation 8. How do I draw the profile on the, because the profiles are very important in heterogeneous systems. If you draw a clear profiles, it is very easy for you to develop the model, kinetic model. In fact, this is called the kinetic model for gas solid reactions. Okay, good. Yeah, tell me now how do I draw that? Straight line. Why straight line? This is correct. Yeah, yeah. I know. Just remember the idli example. If your rate of heating is very very less, you cannot heat anything. So, then entire conveyor belt will have the same concentration of idlis. So, that is why same everywhere you have the same concentration of CAG, right. Okay. On the other hand, if you have the mass transfer control, reaction is very very fast. That means you are able to eat very quickly, and practically you will see on the surface 0 concentration of that idlis. Okay. So, you have to draw something like this, maybe straight line, depends on the geometry. So, here CAS is approximately 0. That is why I have drawn here, I mean I have written here in equation 6. when you have mass, this is mass transfer control. We will write here MT control. Yeah, that is MT control, and this is what I have given here. Always for mass transfer, you will be very comfortable if you write CAG minus CAS, but here CAS equal to 0. And for reactor design expression, I have to use now mass transfer coefficient. There is no more reaction rate constant. And what are the problems we may face with this? If you do not know that there is a global rate of reaction, if you know that mass transfer is not is playing a role in heterogeneous systems, and all this we are talking about only at one temperature. Okay, again heat transfer also comes into picture. Okay. So, if I take that only for isothermal system, I am talking about only mass transfer in heterogeneous system, and you do not know that you have these heterogeneous systems. What do you imagine? You imagine that the rate is proportional to some constant, correct? No, I mean that is what all chemical reactions, the first assumption is minus R A is proportional to C A to the power of n and C B to the power of m. Okay. And those two coefficients you have to evaluate. If n equal to 1 and m equal to 1, then you will have first order with respect to each, overall second order, all that. So, that is why first assumption is directly proportional to concentrations, right. So, that is why even here when you assume the same thing, you have from equation 5, you have minus RAOB equal to K0 CAG, where K0 equal to, what is the number? This is 9, this is 10. Okay. Where K0 equal to, or 1 by K0 equal to 1 by Kg plus 1 by Ks. Right. This one I have written as this equal to 1 by K naught, which will go to the top, and then this is K naught. Okay. Good. Anyway, so this is the equation what you have actually, and you think that this is simply K naught, which is some constant, but this K naught has mass transfer coefficient and reaction rate constant also. And suppose I now repeated, this is for one temperature what we have done all this. Now, I conduct the same experiment with another temperature, like another temperature, because I would like to find out the Arrhenius relationship. But now, if I am imagining that I have only K naught, which is a reaction rate constant, because I have not taken heterogeneous systems. I do not know whether chemical and physical kinetics both will really affect the process. Right. So, under those conditions, I am imagining that I have K naught, and actually that is a combination of these two. Right. So, with the temperature, if I plot okay, here this Arrhenius plot, this is ln K or K naught equal to sorry not versus T 1 by T, then you may get something like this. Or instead of that, I will just plot, and then normally how we behave we will try to see. Okay. So, this one like this you may get the points, right, because I do not know anything about the presence of chemical and then physical factors affecting the rate of reaction. Normally what we will try to do, we are all experts now, going to Excel and now choose that option linear, because you know it must be straight line. So, you simply draw this, which is totally wrong, because there is a beautiful phenomena that is coming here, right. But on the other hand, I will be carefully seeing that why, another time repeating the experiments, and then finally seeing that there is some problem with this, why there is slight curvature. So, if I analyze that, I have to plot like this. So, that means, if I divide this as this zone or also this zone, right. So, here it is almost constant within the experimental error. Why? Mass transfer, and the effect of temperature on mass transfer is not that much. Okay. It comes as T to the power of half, T to the power of 2 by 3 like that, because of the diffusion coefficient. But whereas in this region, when I have the reaction control, now this goes as exponential. So, that is the reason why if you extend this, this will be your normal minus E by R T line. So, you see now wonderful phenomena like empty control here, and this is reaction control. That means, kinetics we are definitely evaluating wrongly if we do not understand the the chemical factors and physical factors that are coming into the rate equation. That is the lesson what we want to I want to tell you here. That is the only point I want to tell you. That means, unless you understand the difference between chemical factors, physical factors that are affecting the rate of reaction, by simply conducting an experiment and then trying to find out the kinetics and using them blindly may make us lot of error, may give us lot of errors. This k value, this k naught, which is actually combination of mass transfer coefficient and reaction rate constant. Okay. If I do not know this, then this I am imagining that as a first order rate equation, like this is the one. This k 0 I am simply, because this is order 1, and here this now I simply take I have the that is equivalent to first order rate constant, but actually that first order rate contains 2 factors. Okay. So, that is the lesson which we have to learn. That means, in heterogeneous systems we have to be careful which is dominating, like mass transfer or heat transfer or reaction or all 3 or all 2, and here if I have all 2, this entire equation I have to use, right. And most of the time for us, luckily we have the mass transfer coefficients available in the form of correlations, that we do not have to do much work now, because any system you take, you have some information or other, unless you want to design totally a new system. Okay. And for new system, anyway, the whole research, the whole work you have to do on your own, and then confirm that what you have done logically right. Good. So, now you can see that what I have assumed here is, here equation 1, it is K s and C A s. Okay. It need not be. That means, here I have taken on the surface the reaction with as a first order reaction. The moment I just change here, I have second order reaction, everything will change. Okay. So, why everything changes? So, the moment I have the second order reaction, assume second order reaction, then that equation 1 is written as minus RaOB equal to Kg Cag minus Cas equal to Ks Cas square. What is the procedure? What is the procedure we have been discussing to find out the overall rate or global rate or other names, measured rate? Eliminate CAS. Now, if I want to eliminate CAS, this equation number 12 I will write. 12. If I want to eliminate CAS, then I have the quadratic equation. Correct, no? I have quadratic equation. So, I think this I will give you as an exercise, and if you solve this and then get as a first you have to get CAS, and that CAS you can substitute either here or here, okay, in any one. So, if you are able to do that, then for second order reaction the rate expression what you get is ROB equal to Kg by 2 Ks, this is 2 Ks Cag plus Kg minus square root of Kg square plus 4 Ks Kg Cag. This is the equation. This is equation number 13. You see now how simple equation. Yeah, and this is the one which you have to use here again in this design expression. Yeah, this here minus ROB, right. So, that is what you have to integrate. And cubic equation much worse, because I think we do not know, you may get various forms like negative, positive, or realistic root, unrealistic roots, imagined roots, all kinds of things. So, that is why you have to really see the effect of physical and chemical factors on the reactor design. I hope now you understood this entire diagram. Every term has a meaning now for you at this point of time. I hope so. Okay. Why? Because input I know. How do you get input? The market survey, MBA guys. Okay. They happily give us, so we will take it. Then kinetics. Now we have to determine. Contacting, you have to choose. Choose in the sense that you have to choose whether you have batch reactor or continuous reactor. And we have already thumb rules for choosing gas, batch system or continuous system. Kavya, remember when do you choose batch, when do you choose continuous? That is why a number of times I repeat, do not worry, I think yeah. Do you remember, Renita?
Reaction types.
No, general thumb rules. Anurag, you remember? When do you choose a batch system, when do you choose a continuous system? I know, because you may not remember when I told you, that is why a number of times I try to repeat.
When we need a continuous output.
Yeah, that is what I am asking. When do you need a continuous system? When do we need, okay? Huh?
Small scale, large scale.
Yeah, that is general one thumb rule. Small scale or large scale. And you also have another thumb rule, particularly for batch systems, when you need flexibility in the product. So, today you may design, you may produce particularly pharmaceutical one drug, next day another drug, next day another drug, like that, or pesticides, insecticides, and also you have the dyes. Suddenly all people may be interested in red color if the movie Red comes. There is some movie called Red. Okay. So, then afterwards if the movie is something about yellow and all green comes, everyone may be using that. So, this industry has to cater to the market. For them it is flexible if you have batch systems, whereas continuous system, once you design, you cannot use it for any other system unless 100% overlap of the parameters are there for these two processes, process A, process B, right. So, that is the reason why once you design continuous system, it is dedicated only to that, unless otherwise you are very lucky to have exactly the same parameters, same temperatures, same controls, then only that is possible, right. So, that already we have that information. I know I am repeating this because it is not your interest to remember, no, it is only my interest to remember, and that kind of silly thing I may not give in the examination. Okay. So, that is why you may not remember, that is why I repeat many times. Okay. So, once you have chosen between batch and continuous, in continuous you have again two possibilities, right, plug flow and mixed flow. So, when do you choose plug flow and when do you choose mixed flow? Abhinav, do you remember, or yeah?
For higher conversion or the same amount of volume.
See, all of us want only always higher conversion. Okay. Yeah, I have given some thumb rules again. Prabhudev, okay, huh? Excellent, good. Why?
Reaction is very fast.
Yeah, the gas phase reactions have very small residence times. In fact, in the form of only seconds. Okay. So, and when I have in the form of seconds residence time, it is very easy for me to provide residence time in plug flow. Plug flow, we know that it is definitely more efficient than mixed flow because of their residence time distributions. That we have to bring residence time distribution. Definitely that is efficient. That is why all of us would like to happily go only for plug flow, but still we do not go many times. The reason is, if I want to provide 8 hours, 10 hours, 12 hours mean residence time in a plug flow reactor, I told you the length may be 100 kilometers, 200 kilometers, because theoretically speaking, what is the velocity which will give you plug flow? Again I am repeating. Yeah, Swami, theoretically what is the velocity which gives you plug flow? theoretically? Infinite. Okay. Why infinite and why turbulent? Tell me, there must be some reason, no? Just imagine plug flow, flat velocity profile, each and every particle spending exactly same time. For each and every particle to spend exactly same time, I should have a flat velocity profile. Flat velocity profile comes only theoretically if I have infinite velocity. Otherwise, still near the wall, you have small droplet, I mean a small drop there. It is not straight line. So that is why. Okay. So when I use very large velocities, if not infinite velocities, then the residence time will be, length should be very large for providing 8 hours, 10 hours length of the reactor. And always plug flow reactor, the diameters are, anywhere you go, it will not be more than 8 inches. 8 inches is maximum. Yeah, 8 inches is really maximum. So generally we will go in industry either 4 inches, 5 inches, 6 inches. And that is why the reason also there is that you have to maintain that flat velocity profile so that you are very close to plug flow. That is the reason why we do all that. So this is the reason why the residence times must be smaller for plug flow reactor. If I have, of course, liquid phase reaction, still the residence time is very small. That means the rate of the reaction time is very small. Still I can go for plug flow. That is again another thumb rule we use. We have a plug flow and mixed flow. Whenever we say that we have gas phase reactions where we have very small residence times required for this reaction to take place, then you go for plug flow. And very large residence time mixed flow is easy for me because it is a tank. So any amount of residence time I can really give if I have a tank reactor, because only length by diameter L by D will just increase. That is how I told you 3 weeks is the mean residence time for wastewater treatment plant. And did you see any time wastewater treatment plant? No, never. Renita, who has seen wastewater treatment plant? You have seen? Yeah. What is the size when you saw that? Huh? Big ponds. Yeah. If it is normal water, we can even swim there. All of us can swim, not only one. Okay. So it is not a tub bath or something. You can really go 1 or 2 laps this side, that side. Really that big. That big is very easy for me because 3 weeks residence time easily I can give there. So that is why. That is why in industry for large productions, even tank reactors will be 1 meter cubed. 1 is not small. 1 meter cubed is very large. 1000 liters. Okay, or 2000 liters. You have to put the size. So that is the reason why tank reactors I can provide any kind of residence time. That is one thumb rule. The second thumb rule also I told you, temperature control. Highly exothermic reactions, even if it is gas phase, but very sensitive. Okay, that means one temperature, 1 degree, that way this way we may catch fire. Okay. So I mean that fire definitely we have to avoid, otherwise you will not be there, or the persons working in the industry will not be there totally because explosions, right. So that is why under those conditions we can again go for a mixed system. One of the beautiful examples are phthalic anhydride, I think to produce nylon or so. It is a catalytic reaction, but highly temperature sensitive. It is a catalytic reaction. So first they tried packed beds, but when they tried packed beds, it is very difficult in the sense that temperature control. They are really worried. Every time when they go to the plant for operation, the operators must go to 10 temples at least, and then pray the god and then go to the industry. Otherwise there is no guarantee that they will come back safely. Even then there is no guarantee, but it is only okay, but only for our safe, for our confidence we go there and then pray and then come back. Okay. So that is why there they have gone to fluid aged bed, where fluid aged system gives some kind of mixing. Temperature control is beautiful there. In fact, the same story what I have told you is also given in 11th scale gas solid systems, catalytic reactions. Okay, so that is why. So now we know that when do you choose batch system and when do you choose the continuous system, and of course when do you choose plug flow, when do you choose mixed flow. Please do not forget this. Okay, please do not forget. I think in a number of times I can repeat. I will be repeating, but next time when I ask you, please answer that. Right, but I think by repeating, of course, I do not blame you, that is why I am repeating most of the time, and at least this diagram we should thoroughly understand. I say all other things are details, calculation of volume if I am using mixed flow or plug flow or batch reactor, that is the detail later, but right now the concept of that, what are the things that are involved in the diagram, right. I hope input we know, contacting when do you choose between batch and continuous, and in continuous again when do you choose mixed flow and plug flow, that we know, and this one is kinetics, next one kinetics and chemical and physical kinetics. The meaning is chemical and physical kinetics meaning is the steps that are involved, the steps that are involved. Here I have actually, that is in the last class I have given those 3 steps and all that, that is what I have not written here. So, in the last class we have written there mass transfer from bulk to the surface, then the rate of reaction, then diffusion of oxygen CO2 back. But because it is irreversible reaction, oxygen coming through the film will not affect my rate of reaction. If it is a reversible reaction, the reversible reaction depends on again the product concentration also we are going to be. So, I know here it is minus R A equal to K 1. So, that you can remain K 2 C B, right, reversible reaction, this is K 1 and K 2. Yeah. So, if I have a reversible reaction, the product also affects, C B is the product, B is the product. So, but here in this example I have CO2 coming, but CO2 is not participating in the reaction, that is the reason why I have to take only 2 steps, mass transfer to the surface, rate of reaction on the surface, and under steady state conditions both must be same, and those 2 we have written here. This is the procedure for all heterogeneous systems. I have given one, but I think in the tomorrow's class I will also just draw the profiles for another 2-3 systems, so that you are familiar with simple drawing, profiles, and this imagination is a must. I tell you, please open up your mind and then have this imagination. Like I told you here how the carbon is burning, you take one particle and there is a flame, and anyway fluid mechanics will tell me that there is a film which you can't see around this, but oxygen has to diffuse because oxygen is not available on the surface, it is available only in the bulk, it has to go through the film and then reach the surface. Then on the surface you should have sufficient temperatures and conditions for reaction, then rate of reaction takes place, then the product gases will come out. If there is no product gas, no problem, that is fine, okay. And so many steps are involved. Out of that, what are my important steps and how do I show them as pictures? All this is imagination what I have done, and now this is the picture, and this picture leads to me just to draw the profile graph, right. This is the profiles, like that I may have some 3-4 steps, and everywhere I have to draw the profiles and list out what is step 1, step 2, step 3, step 4, and you will see here most of the time reaction is only 1 step and mass transfer steps can be 4 or 5. That is why mass transfer is so important in heterogeneous systems, particularly if you take our Dalda reactor, slurry reactor, there are 4 or 5 steps involved, and you take normal catalytic reaction, simple catalytic reaction. If I have this is the particle, and similarly the reactant is going, that A going to B, and it is not reversible reaction, we assume that it is irreversible reaction, catalyst particle A is going around. So, now this A has to diffuse through the film first, because the reaction is taking place only inside the particle, because this is porous particle. Here at least we have assumed it is a non porous particle, right. So, I have the particle and then going around this, and you have now first step is mass transfer through the film, second step is it is a porous particle, mass transfer is through the pores, and when it is going through the pores it will also get absorbed, and if I look at one molecule, this one molecule has to go from bulk to surface through the film, step 1. Step 2, it has to diffuse through the pores, and after diffusing some distance it has to get adsorbed. After adsorption it will form a complex and all that people say, and then afterwards it will get dissociate and then product is formed. That is reaction, adsorption and then reaction. After reaction the product which is formed there has to dissolve. So, that is 5, and after dissolving it has to come out through the pore, that is 6, and then it has to again come out through the film to the bulk, 7 steps. Which one is controlling? We do not know. That is why in heterogeneous systems the kinetics is really hell. That is why happily we ask chemists to do that. Okay. You develop Langmuir initial wood kinetics, Langmuir initial wood kinetics will give you all these 7 steps, and we are also going to derive some of them, and I will also show you at the end one all 7 controlling what kind of equation you get, all 7 steps controlling. And unfortunately in all this is that you have these constants, Kg, Ks. In this catalytic reaction you have 2 mass transfer coefficient steps, okay, and then adsorption, desorption, all these constants, surface reaction, all these constants are involved there. So, you have to determine from the experimental data these constants very, very accurately. That is why chemical engineers are also should be very good mathematicians. I am not saying mathematicians to develop new theorems and all that, but at least for using the mathematics that are available at least with us. So, in analyzing our data, and you know how difficult it is to evaluate this constant K1, K2, K3, K4, more than 2 we have always difficulty in evaluating the constant I am telling. So, how do you find out? Normally I have the rate equation, I have the experimental data. Now, rate equation has K1, K2, K3. Now, I have to fit this entire data to give this K1, K2, K3, right. MATLAB is one which will help us, right, and then the MATLAB we will go and then we will give some guess values and it evaluates K1, K2, K3 and then gives you. You bring those constants. Then I have also done the same experiment and same data. In fact, I also want to analyze using this K1, K2, K3 to evaluate, then I will give a different guess value. Then my values and your values may not be unique. That is a physical system. It must have only one unique set of values. This is what is the biggest problem if I have more than 2 parameters. That is why Leonspiehl beautifully tells that you may produce any number of wonderful models for publications, but for industry you should give at least the minimum, one is the best one or 2 parameter models. He never complicates things, because the moment you go more and more 4, 5, 6 and all that, I do not have any physical meaning for that, no physical meaning for these values. Okay. I think I have already told you some time back, maybe residence time distribution. I do not know, Anurag, did you do CSTR with dead space and bypass, a model for CSTR or mixed flow with dead space and bypass? You are not doing the okay. There you will have 3 parameters which is called a bypass fraction, a dead space fraction, and dead space is not really dead. Definitely there will be mixing some kind of exchange between dead space and active zone, what we call exchange coefficient, all these 3. Bypass has a definite meaning, 20% bypass, 30% bypass, okay. And what is the other one? Dead space has a definite meaning, maybe 10% dead space or 20% dead space, 100% cannot be dead space, okay. That is a very bad design, okay. Yeah. So, then this exchange coefficient depends on what kind of mixing is going on, 3 parameters. So, if I evaluate data, if I get a set, and if you evaluate, if you are getting a different set, what is the physical meaning for this? I may be telling that I have 15% dead space, you may come up with 30% dead space, but that system at that particular conditions, it must have only one set of values. That is why that uniqueness in evaluating these constants is one of the biggest challenges in chemical engineering. Even if you do research at high funda level, when you have more and more, I do not know how really I will appreciate these biotechnology people, where they will have 25 parameters, and mechanical engineers for combustion 400 parameters for combustion. Okay. Really, if you see that there are so many models with a lot of constants, I used to wonder how are you going to evaluate all these 400 parameters, 400 constants. So, that is why as engineers we should present our system, the experimental data modeling should be as simple as possible, and beautifully Einstein told that model can be as simple as possible, but not simpler, Really, it is a wonderful statement what he has made. You can make your model as simple as possible, but not simpler. So, that we have to remember, and then I think I will give you some examples in the next class, and after the next class then we will go to non-catalytic reactions first. I think I have not told you how do I evaluate you till now, because I thought I will give you this introduction for that particular figure and then tell you that